A very good evening, everyone. A warm welcome to MazeX 1.0 workshop number 3. We are excited to have you all here as we kick off this incredible journey into the world of Micromouse robotics. This workshop series is designed not just to teach, but to guide you step by step towards building, competing, and excelling. Today, you'll get a clear overview of what lies ahead, from the structure of the competition to the fundamentals of PID control and wall following techniques, along with what you can expect in the upcoming sessions. So, stay tuned, stay curious, and get ready to learn, experiment, and innovate. Moving on. This event is designed to combine learning, innovation, and competition through robotics. It's a hand on experience where you'll explore intelligent systems and develop practical technical skills. Throughout this series, you'll also improve your problem solving abilities while working in a collaborative environment. Overall, MazeX 1.0 is not just about building a robot, it's about gaining real world engineering experience and learning how to think creatively. So, now let's take a moment to introduce the experts who will be guiding you today. We are honored to have our two amazing speakers, Mr. Kavishka Jayakody, a third year undergraduate at Electronics and Telecommunication Department, University of Moratuwa, and an intern in Embedded Systems. And Mr. Rajinthan Rameshkumar, a third year undergraduate at Electronics and Telecommunication Department, University of Moratuwa, who is a research intern at Satellite Technology and Research Lab. Their insights will be incredibly useful as you begin your Micromouse journey. So, to continue our session, I would like to invite Mr. Kavishka Jayakody and Mr. Rajinthan Ramesh Kumar to continue the session.
Okay. Hi everyone. Thank you, Akshi. Before moving into the session, uh, for those for those of you I have met, my name is Rajinthan, and I'm also a third year undergraduate, just like many of you. But not too long ago, I was exactly where you are right now, uh, wondering to make a micromouse and compete in a competition. And recently, I competed in one especially RoboFest micromice competition, and I can tell you firsthand that the most frustrating part is not building the hardware. It's actually tuning the software for it. Okay, then let's move to the presentation. As Let me share my screen. You can see my screen, right? Can anybody confirm?
Yes, Srikansh.
Okay, thank you. So before before moving to the PAD, why we need to have a good control algorithm. So let me show you some videos. One minute.
So here here is the mouse that I built and this is the video before tuning the PID well. So here you might not notice the wobble here, but if you closely watch this, you can see this is not going in a straight line, right? So here you can see some wobble. So here the issue is not the hardware; it's actually the algorithm that it's running on its hardware. Okay, so here you can see that after this cell, this is entering this cell not in exactly in the center. So here you can see this is not aligned in a one cell movement. It is going uh it's going with a offset error and it's hitting the wall because of that error. And if we go to the other video, you can see the same mouse but with the correctly tuned PID. It could go around the maze without hitting any wall. And if you notice this correctly, here you can see that here you can see that the mouse is entering this cell with an offset error, but within a single cell, it's going to the center before moving to the next cell, and it's correcting its orientation in the very next cell. So with a good PID, with a good tuning and a good wall following algorithm, you can make a bad hardware to run smoothly without any collisions. So that's why we need to have a good control algorithm. So that's what we are going to discuss about in this session. So if we move forward, so before going to PID, what should we need to be? We have to make sure to have good inputs to the PID. So for that, we need to have good distance readings from the mouse to the walls. So for that, we need to have at least four sensors, two pointing towards to the sides and two pointing towards the front wall. So first, let's talk about the side sensors. Here you can see we have left two sensors on the both sides. The left side sensor is pointing towards the left wall, and it's not perpendicular to the wall, right? So
And you need to be clear about why we are having this angle. So for the PID algorithm, for the PID algorithm, uh, we should give a linear uh, input to the PID algorithm to get a proper output. So if we have these sensors very perpendicular to this wall, imagine the case where the mouse turns left. So if it's very perpendicular to this wall, if the mouse turns left, then you might get the distance the distance increases with the movement. Also, even if the mouse turns right, at the same time the distance will increase. So you won't differentiate whether mouse is moving left or not. So that's why we are having this sensors with a around 20 to 30-degree angle to this one, right? So in this case, if the mouse moves towards left side, then the distance will decrease, and if it moves right side, then the distance will increase. So then you can feed this distance feeding to the PID algorithm, and the PID can handle this linear effect and give you proper commands to the motors. So you should make sure to pay attention on these little details. Otherwise, you might get you might have good PID algorithm, but with the bad sensor input, you your mouse will fail. Okay. If anyone have any doubts, so if you want to clarify something in detail, just put in the chat so we can discuss about that. And so you might have questions why we need to use a IR sensor for the distance readings and how to use them. Since these IR sensor readings won't give you a proper direct distance from the mouse to the wall. So we need to we need to uh, we can discuss about that later. Before that, uh, how do you get the readings from the 4 year sensors? If you are using top sensors, then you might not need to worry about much, but the top sensor readings may take 20 milliseconds to get a single reading. If you're going to have four sensor readings, it may take if you run it parallel, you can have it 20 have it in 20 milliseconds, but still you can only have a control loop at only about 50 hertz, but it's always recommended to have at least 500 hertz of refresh rate. So that's why we have to go with this IR sensor. And also in this IR sensor case, you have an issue like the sensor crosstalk. If all four sensors of all four IRs are turned on, then the receiver can pick up the light from the adjacent IR lights. So to accommodate that, we have to individually control all IR sensors. Like first, we have to turn off all the IR sensors and turn only the IR LED that we need to measure, and then take the reading and then turn off. So here you can see the timing diagram. So first, you have to take uh, all four sensor readings without turning any IR LEDs. So in this case, you have to turn off all IR LEDs and take the ADC readings for all four sensors. Here you are measuring the ambient light effect. So in this case, even if you have other IR sources like ambient sunlight or the focus lights that may emit some sort of IR light, so that can add, add to the noise and affect your PID performance. So that's why you have to subtract that noise from your sensor reading. For that, you have to get the ambient light reading with all the IR LEDs turned off. Then you have to turn on only a single LED. In this case, you can turn on this left side's IR LED. So this will emit the light. So this will emit light and that will reflect off this left side wall and get back to the sensor. So this this IR sensors may take 100 microseconds to have the full exposure. So you have to let the IR sensor for that exposure time. So that's it. That is roughly about 100 microseconds. So after that time, you can take the sensor readings, ADC readings. You can use your ADC to take the reading and subtract the ambient light. So in this way, you can subtract the ambient light noise from your readings and get the raw ADC
uh, readings, and you can turn off that LED and move to the other sensor. So in this way, you can have a good reading without ambient light, ambient noise, or any other sensor crosstalks. And but in this case, you might think like you are wasting so much time to get the reading in sequential way. But if you closely pay attention to this whole four readings only take about 800 microseconds. But your top sensors, single top sensor readings might take 200 milliseconds, 20 milliseconds. In this case, it's only 800 microseconds. So this is less than one millisecond. So it's 20, more than 20 times faster than your top sensors, time of flight sensors. And so that's why most of the fast micromousers are using this kind of IR LED and sensor pair for their sensors. But here you have a catch. The time of flight sensors give you the direct exact distance readings, but here you only get the light intensity. So if the wall is very close to the mouse, then you will get more light to the sensor and you will get higher ADC reading. And if the wall is too far away, then you will get less light intensity to the sensor and you get lower ADC value readings. So how do you get the exact distance reading from these ADC values?
So in this case, if the wall is too far away, the light intensity is getting lower. And if the wall is here, the sensor will pick up more light. And this is in an inverse square relationship. Like the light intensity read by the sensor is inversely proportional to the distance square. So you can see the distance versus ADC value reading in this graph. So if the wall distance is too far away, the light intensity is too low. And if you come closer, then see that the IR sensors are picking up is exponentially increasing.
So this is not a linear relationship. So you have to convert this to a distance reading. So how can you convert this? So I hope everyone understand this graph, right? So if you want to confirm that, you can check uh, whether you can find the reading for the distance 60 millimeter. So if the wall is at 60 millimeter, what will be the ADC value? If you can figure it out from this graph, then you're good to go.
I hope it's clear for you guys. So you understood why this is not linear. So how you can convert this to a distance area? So if your ADC value is in example 1050, how do you exactly calculate the distance that 80 millimeter from that ADC value? So here you can see that light intensity is inversely proportional to distance square. So you can say that the ADC value is related to the intensity, light intensity. So ADC value is nearly equal to a constant over d square. So how do you find this constant? So that's the main issue. So each of your mouse have each of the sensors, even in a single micro mouse, you have four sensors, and all the four sensors might not have the same constant. So you have to find that constant. That's why we do a calibration. Uh, that's why we do a calibration before the run. So first you will place your micro mouse in a three-sided set. So usually the first cell, the starting cell will be like this. You have three sides, and you have to place the micromouse in a known distance from the front cell and very center from both sides. So you will exactly know what's the distance of these cells, and you know also distance from your arrangement, and you can have this written in your code. So in this case, you know this distance. So your distance is known, and in the calibration round, you will take several ADC samples and take the average. So now you have the average ADC. Now you can find this K, right? So in this way, you can find this constant and save it in your memory. So for the rest of the run, you know the constant, and you will measure the ADC value, and with this relationship, you can find the distance. Okay, so from these uh, from these simple IR sensor and receiver pair, you can find the exact distance in sub-millimeter accuracy. Actually, I tested this and it worked for me. That's why I'm recommending this way. And it only takes less than 1 millisecond, and you can subtract the ambient noise and everything. So this could be a better way, but you need to make sure you can control all the IR LEDs individually. So that's how you can uh, eliminate the sensor crosstalks. So in this way, you will find the exact distance from the wall to the your micromouse. So then you can go towards the controller, the PID controller, right? Uh, if anybody has question or anything to clarify, just let me know quickly so I can discuss that briefly and move towards the next part. Or else can anybody confirm whether it's clear or not?
It is clear. Miss.
Okay, thank you. So after you getting these raw ADC readings and then convert that to distance reading using inverse square law, now you can move towards the wall configuration and wall following part. Okay, so before moving to the PID, we should know where to use PID and how to use them, and what are we going to correct. So what's the error term here? Okay, so we have actually six different cases, but only a single number we have to get. I'll explain how it's done. So this is your ideal case. Your micromouse in the center, uh, and it's not having any of it doesn't have any offset error or angle error. It's perfectly in center, moving forward. So in this case, if the like wall distance and the right wall distance is equal and it's only 90 millimeters, you find that there's nothing to correct, right? So you can just move the micro mouse forward. You don't have to turn or do anything. So in this case, uh, you don't have to do anything. The next case is your micro mouse is drifting right. So because of the motors mismatch, like this motor is having less friction than this one, so this move towards right, or else the friction on the wheels might be different. So in kind of these situations might make your mouse to drift towards the right side. So how do you identify that and correct it? So you only have your mouse only knows what are the distance between your four sensors to the walls, and what's the speed of the motor it's driving currently. So that's the only detail that your mouse has. It- Your mouse can't see it from the top view. So you only need to use these sensor readings and command the motors to align it properly, right? So in this case, you don't have to worry about the front sensor reading. So you only have to focus on the left sensor and the right side sensor reading. So you have the sensor reading to the left side wall and right side wall. So in this case, how we usually do is we simply subtract our right sensor reading from the left sensor. So if it's moving towards right, then the right distance will decrease and the left distance will increase. So this case, if you subtract this from the left sensor reading, you will get the number 120. Okay. So the left distance is 150 millimeters and right distance is 30 millimeters. But your micromouse is only having a offset of 60 millimeter in the x direction, positive 60 millimeter in the x direction. But if you subtract this from this, you are getting 120. Note this number. You will need this in the later slides. We are having only 60 millimeter offset on the x direction, but you are getting 120. Okay, so the same will happen for the left side drifting. So if your micromouse drift towards the left side, your distance will decrease on the left side, and your distance reading on the right side will increase. So if we subtract the right side distance from left side distance, you will get a negative number, but you are getting the double the amount of the actual drifting. Okay, so in both three cases, we are subtracting the left distance, sorry, the right distance from the left distance. So you are getting different values and for the different scenarios. So if you are in the perfectly center orientation, you don't have to do anything. So that's why your error term is zero. If you are drifting towards right, your error term is positive 120. So you have to fix this. To fix this, you have to reduce the error. To reduce the error, you basically turn towards left side. So if you have a positive error, you have to turn your micromouse in left side. And if you have a negative error, you have to turn your micromouse right side. So this can be done easily on later parts. So in these three cases, you have walls on your both sides. So this is easy, subtracting your right value from left value while you have both the readings. So what if you don't have a single side wall, or you only have access to a single side of wall, or else you don't have any wall, like both the sides are empty. You can find these cases also. So how can you handle this? First, uh, let's take the example. You have only the left wall. So you only have the reading of the left wall to your micromouse, and you, according to your algorithm, your right side reading will be infinity. Why? Because your ADC will uh, read zero because you are not receiving any light from any reflecting light from any walls. So your ADC value will near to zero. So if you use the inverse square law, you will get near infinity value. So you can just neglect that value. Only you have reading for the left wall. So how do you find the error now? In example, if your mouse is offset positive 60 millimeter on the x direction, your left side wall reading will be 150. Why? It's 90 plus 60, so you will get 150. But what's your target value? Should be 90, but you are having 150. So you can just use your target value to find the error. So your target value is 90. So you have to subtract that left distance reading 150 from your target value. Okay. Uh, you have to subtract your target value from your left distance reading. So this should be plus 60. You always subtract your right side value from the left sensor reading. So always left sensor reading should be on the left, and you have to subtract your right sensor reading. If you don't have the right sensor reading, you can subtract the target value. You can put target value instead of the right sensor reading. So you should get positive 60. So this should be corrected. Uh, so this should be positive 60. And here you can notice instead of positive 60 millimeter offset in X direction, you are getting 60 on this case. But if you have both the walls for the positive 60 offset, you are getting 120. So you have to closely pay attention to this case. So the scenario is same. The mouse is 60 millimeter offset from the center, but you are getting different values for different wall availability cases. Okay, I'll explain that later. Just remember these numbers. And the same happens for the right wall only case. So you will just subtract your right uh, distance value from your target distance. Your target distance is 90 minus your right distance 150. So you will get negative 60. Okay. Sorry for this. I just ignored this signs. So it should be negative 60. So if the value is negative, you have to turn your mouse into the right side. So this is the case for the two wall cases. If the value is negative, you have to turn your mouse to the right. If it positive value, you have to turn towards left. So you have covered five different cases, and this is the sixth case where you don't have any walls on either sides. Okay, so how do you handle this case? You have infinity value here and infinity value here. The left sensor is reading infinity distance and right sensor is reading infinite distance. So if you encounter this case, you just give array as 0. Like you assume that you are perfectly at center and your mouse should go straight forward. Even if you have any misalignments, you have to you don't have any choice. You can't do anything to correct this at this case in a simple scenario. So the mouse will go to the next cell, and if it finds any walls on that cell, it can follow, it can come to any other previous cases and follow the wall. Otherwise, you don't have any choice. So you just simply pass 0 as error. So the mouse will continue moving forward. Okay. So we have covered six different cases with three cases with both walls are there, and three cases where you have only one way, one wall or no wall at either sides. So you can write the algorithm covering all these six courses in this simple way, right? So in this algorithm, all the six cases are covered. So I'll explain these parts briefly. So here you define a threshold for the walls. So if the wall distance is above this threshold, you assume there's no walls. So your ideal case is 90 millimeters. So we give a certain margin for us and we set 27 millimeter as threshold. So if your mouse uh, sensor reads above 27 millimeter, it assumes there's no wall. Okay, and your left target and right targets are 90. So this is the ideal case, and your whole function will return the error value. So this is the function that returns your error value as a float. So first you have to compute the error by passing your left sensor reading and right sensor reading. So your sensor readings are handled by another function and it will pass only the values here. So if you pass your left sensor reading and right sensor reading, in example, if you pass 150 millimeter here and 30 millimeter here, so the first it will check whether there's a wall or not. So the 150 millimeter is less than 270, so the wall is there, and 30 is also the same. The right wall is also there. So this is the uh, case where both walls are present. So if you, in example, if you pass 400 here, then this condition will fail and it will result in false. So that means there is no right walls are present. The right wall is not present there. So that's how it will check for the uh, whether it falls under first three cases or the last three. So this is the first three case scenario. So if both walls are present, then you just simply subtract your right side distance from your left side distance. So this will uh, give you the error value. That so so this is the scenario for that case. So you just simply subtract your right sensor distance reading from your left sensor reading. So you get plus 120. So this is your return that you are going to return to the PID part. So here you only calculate the error. So that's the function explains. So here you just subtract your right sensor distance from your left sensor distance. What if you don't have the right ball? So if the right ball is not present, then you just use your left sensor reading and your intended left sensor target reading. So this is 90, it should be 90. So if you read 30 as your reading, you are subtracting 90 from it. So you get minus 60. So you will pass this minus 60, but closely pay attention here. You have to multiply it by 2. Why? Here you are your only the left sensor reading is varying. So your error is not double as this scenario. In this case, if the left sensor reading is decreasing, the right sensor reading is increasing. So you get area double the amount of this value. So that's why we have to multiply it by 2. So that's why I said you to focus on these numbers. Here you are having only uh, 60 millimeter offset, but you are getting this same 60 as the revenue. But in this case, you are having the same 60 millimeter offset, but you are getting 120 as the error value. The magnitude is double the magnitude of the offset error. Okay, so that's why you have to multiply the error value here by the factor of 2. And the same happens for the right ball only case. You only have the right ball, no left ball, so you only use the right distance reading for the error calculation. So in this way, you will get the linear error reading for all six cases. So if you don't have any walls, you just return zero, assuming you are exactly in the center and you can just move forward. Okay. So this single function will handle all the six cases and give you the perfect error value for the PID calculations. So you can pass these values for your further calculations, and then you can move towards the PID. For the PID explanation, uh, I invite Kavishka to explain that. Over to you, Kavishka.
Um, Hello, I'm Kavishka. So I'm also a third year undergraduate from Electronics and Telecommunications Department. And why I can do this presentation is that we made a Micromouse in 2024, and it had some sort of a winning, not the first, but some place at a good Micromouse competition. And for that, we had to go through some theories and hardware related things for the Micromouse building and programming and computing. So I think it's a good start and a good experience so that I can share the experience with you. I'm going to share my screen. Can you see the screen? Hello.
Yes, we
Yes,
can see.
Kavishka. We could.
All right. All right. Before moving on, I need y'all to think about systems. Systems in the sense, for this Micromouse competition, we'll have a system of a motor and a motor controller, which is using PWM. Think it's using PWM for the driving of the motor. All right. So if we give a 50% PWM signal for the controller, the motor should spin at a certain speed. So we can measure that speed, and then we can change the PWM input, and also again measure the speed of the motor. Likewise, we can map out the entire PWM range, and then we can predict the output for each PWM value. But will the PWM value and the motor output be same for all conditions? Think of that. So, will the motor output be a direct relationship of the input PWM signal? And that gives us a way to the next slide, the open loop systems. So in my explanation, I'm going to tell you about general control theories and general systems to be controlled, and then you can map that out to the wall following. But this PID is not strictly limited for wall following applications. It can be used for speed regulations, torque regulations, force regulations, and for for various applications. So this PID theory is the first formulated to control the ships movements, uh, like that. So back to the topic. Uh, Back to the topic about the motor. So we have some input signals, and then we have a controller. So this controller we can assume as the motor driver, and then we have the plant. That's the motor that I told you before. So if in a perfect world, this input PWM signal is directly proportional to the output of the motor, that means the motor speed, then the world will be very easy to control. So there we will not need robust control algorithms. So the motor behaves as we need by just giving it inputs, and likewise the vehicles, the electric vehicles, all the fuel consuming vehicles, all the control systems. Designing the control systems will be very easy, but it's not the case. We have voltage drops in the batteries. We don't have identical motors for the systems. And regarding our Micromouse situation, each sensor will be different from each other. The maze will be different from one place to another. So we can't just give inputs only to the output plants. That means the actuators, and just hope for the system to react as we need. For that, to minimize the effects of that and hoping the plant, that means the system, will behave as we need, we are going to have feedback systems. So the feedback systems are systems where the system output is monitored, and the input commands are adjusted according to the output. So we we need to control some system, and we give the expected outputs we need from the system, and then the controller looks at the output of the system and adjust the internal conditions appropriately to give out the expected output that is needed. So for that, I'll give you a good example. Um, uh, think that you are in the middle of a road. So this example is kind of related to the wall following as well. Now think that you are in the middle of a road, and the road is straight. There are two white lines in the edges of the road. So it's maybe a carpet road with the white lines in the sides. It's a straight road, and you are in the center of that road, and your eyes are blindfolded, but you are kept such that your trajectory, your path will be just parallel to the straight road. So if you move perfectly straight, you'll end up at the end of the road. Now think what will happen if you move in that road. Will you be able to go straight to the end of the road, or will you stumble upon the edge of the road? You get out of the road in the way. Think of that and tell me what will be happening. Anyone? You can imagine, and all of you will get that. For 100% accuracy, you will not end up in the edge of the road. You will not go straight in the road, but you will end up in the side of a road, maybe in a drain, in the side of the road. So open loop systems like this are just like that. It's like a system that's blindfolded. It does not know, it does not feel what it is doing. It's just reacting to the inputs without looking at the outputs. To minimize the effects of that, we are introducing closed loop systems. So the closed loop systems happens to get the outputs sample the outputs of the system and then feedback again to the controllers. So this is a block diagram of that. So the feedback systems, the closed loop systems, those two are same, uh, makes the dumb machines into sensing systems. So, and it bridges the gaps between where it is and where it should be. Now back to the blindfolded road walking kind of thing. So if you are not blindfolded, you can look at the road sides. You can look at the lines that are drawn in the road. I mean, uh, like for just now, think that all the other world, all the surroundings are just vanished, and you only have the road. So if you can see the lines beside the road, then you can definitely go straight in the road and go to the end. But if you are blindfolded, then it's not possible. Now think you're blindfolded, but occasionally you can open your eyes and see the road occasionally. Now the conditions turn a bit favorable for you to go to the end of the road in the in a straight path. So occasionally you check the white lines beside the road and correct your course of walking or running. Now you can uh, reach the end, and now think of something like this. Like Rajinthan said before, we can define a error function. So the error function is how much far away you are from the middle of the road. How much far away you are from the middle of the road. So function like that. So look at the error in the road. As Rajinthan mentioned, so the term set point. The set point is described as the perfectly center in the corridor. In the previous case, as Rajinthan mentioned, it was, I think, 90 centimeters from the walls. Now, in this example, it's 1, but it can be anything, any set point. It can be a speed, it can be a position, it can be a force. In our case, it's a position from the wall. So we can define the error function as the set point minus the measurement. So Rajinthan previously mentioned how this measurement is taken from these IR LEDs. If there's a wall in the left and right, if there's a wall just in the left, just in the right, those cases. That's it. So we define an error function. And now, in the same example that I told you about the road, you're still blindfolded, but there's a friend looking at you and telling how far away you're from the center point. So there's a friend, he's telling you're far away, move now. You're far away, move to the left so that you are in the center, or move to the right so that you are in the center. So he's telling if the deviation from the center is very high, he's telling to move aggressively towards the center. If the deviation from the center point is low, then he says your distance from the center point is very little. slightly move towards the left or right. So the friend shouts. The friend shouts, "You're far away. Move to your left. Move to your right. Move aggressive to your left. Move aggressive to your right. Or slightly move to your left. Slightly move to your right, so that you are in the center." Now, just think with, just think along with me. You're still blindfolded. The friend shouts at you to direct you to the center, but will you walk in the center of the road? Probably, even as you think, you will not be able to uh, just walk in the straight, I mean the center of the line, with your friends help, with just the screening of the deviation from the center line. So you'll be going past the straight line to your left, and then the friend shouts that you're too far away from the center to the left. Move to your right, then you move back, passing the center, then you overshoot, and then the friend shouts again that you have passed this line to your right, move left. Likewise, you'll be oscillating around the center, but you'll not eventually reach the center point. So there are many things that affect this as well. Your walking speed, whether you are running, how accurate your friend sees your movement, and how quickly you respond to your friends instructions, like things affect how good you'll come to the center of the road. And then there's another friend. He's telling you how quickly you're making the changes that the first friend is telling. So he's telling, "Careful, you're approaching too fast. Slow down." So think you are in this point. The first friend shouts, "You are in the, like, say this is right side. Sorry, say this is the left side. Say this is the right side." The first friend shouts to move to your left aggressively. So you quickly move to your left. Then he tells to move to your right, move to your left, move to your right. But there's another friend. He's telling, uh, you're moving too fast. You might fall. You might pass the center point. Uh, likewise. So with the help of that friend, you can minimize how far you will be going passing the center line. Now think like this. So this is the center point. You are in your right side. So to fill this gap, you're moving fast, and the second friend tells you you're moving too fast. Slow down when you're changing, your speed is high. Likewise, by that means you'll be moving in a path like this. You'll be moving in a path shown in the blue color one. Why? Think of these increments. I mean the tangents of these. So at this point of the red color line, your error is very high, so you start moving aggressively. But the second friend says you're moving very fast, slow down. So now you're slowing down, and the second friend still keeps saying, okay, now your speed is good, and the first friend is saying, you're still not in the middle, move to your left. And the second friend is adjusting your speed appropriately. Okay, you're moving too fast. Okay, you're in a good speed. You're moving slow, increase your speed. Likewise, the two friends help you guide to the center of the road. So I'm telling this very fast, but after the workshop, if you need to understand the PID properly, you can use this example to get some idea, get a practical idea of what this is. And then we have another friend. So that friend is telling that you are very close to the center, but you are not exactly at the center. So he's looking at you for quite some time, like not as the previous two friends. He's observing you for a long time, and then telling that if he's not at the center but very close to the center, he waits for some time and tells that you have been walking for like uh, 10 minutes off from the center this much, like few centimeters, and then he tells you have to correct that so that you are in the center of the road. uh, with the help of that friend and the previous two friends, now you can get exactly into the center of the road. Now look at this picture. So if these friends are not here, if these like, think this is the road, this is the center line, this is the left side, this is the right side. So you start from here down here, there's no friends. You're blindfolded and you just follow the direction which you're facing. Think you're facing to this side. So you start walking and you'll get some uh, pain in the legs. You just wobble to your right or left, then you start going in various directions, and somehow you end up in a drain. And then you got this friend who shouts that the first friend who shouts you're moving away, move to your left or right to get to the center. So you start going in this path, and then you have another friend that tells the second friend, he tells that you are moving too fast, slow down, you're moving too slow, speed up, that kind of thing. So you'll be going in some path like this green color one or the blue color one. But we can't be sure that we are reaching the center line. Like imagine this is the center line. You will be going very close to the center line, but not exactly in the center line. So then the third friend comes and tells, you have been walking 10 minutes just near the center line, but not exactly in the center line, just a few centimeters, so that you are in the center, like that. So with the help of these things, you can get a good enough system to to work as the to work as a system that gives the exact output it is expected to deliver. Uh, are there any questions on this, on the concept, on the example? Uh, do you guys see any relation about the things that I said now and its relevance for the control systems? I mean, not just for the wall following, it can be used for motor controlling things as well. So are there any kind of misunderstanding, anything that you need to know? Uh, If you have, so just put in the chat, and I assume that you don't have things to be asked just right now, and I'll be moving forward. If you do have a question, just put in the chat. We'll look at them at the end of the session. All right. Then I'm just covering the theory parts. I'm not going to talk very much about wall following or any controls specifically. I'm just getting you the basic theory parts without very much mathematical explanations. And for the control systems, we have a few states. We have few states that defines the control system. So the control system, now you know what a control system is. It's a closed loop system which runs on a input, gives control signals to the system. The system gives an output, and the controllers sends the output and adjust the inside control logics in the inside control signals accordingly to give the expected output. So it's a control system. So the control system, as I said, has three states. It's the underdamped state, the overdamped state, and the critically damped state. So what's an underdamped one? So in an underdamped situation, the system oscillates, or the system oscillates uh, around the set point. So the set point is the expected, not the observed, the expected output from a system, and the output just oscillates around the set point. And then we have an overdamped system. So the overdamped systems are not oscillating around the set point. It reaches the set point exactly, but the time it takes to reach the set point is pretty much high. So back to the road example. So the friends are telling you things, move left, move right, you're moving too fast, you're moving slow. So you have committed an error for a long time, just adjust that. So with all those systems, you're moving towards the center. You're definitely moving towards the center, but it takes a very long time. That's an overdamped system. The system is sluggish and slow correction. And then we have critically damped systems. So the critically damped systems, it's also somewhat like an overdamped. I mean, it's not overdamped, but it's like an overdamped system. But that system, the output reaches the set point with the minimum delay, with the minimum time it reaches the set point. So a system like that is a critically damped system. Like we can have this picture explain that as well. So we have this underdamped system. So in underdamped systems, we can assume, I mean, not exactly, but we can assume that the P controller is dominant. I have still not told those things about P controllers and all those things. I'll tell that and come back to this after. Okay. So we can map those friends that I explained before, the first friend, the second friend, and third friend, into mathematically described terms. We can map those friends. I mean the behavior of those friends into mathematically described terms, and we can express it as something like this. So the first friend represents a proportional term, and the second friend represents a derivative term, derivative action, and the third friend represents an integral action. Why I am saying that? The first friend is telling, oh, you are far away from the center. Move towards the center. Move to your left so that you are in the center. So he's looking at the error from the center of the line, and just directly telling you, to make the corrections. And then the second friend is observing your rate of change of your error, how quickly you're moving towards the center, how quickly you're reducing your error. So looking at that, the second friend gives instructions for you to adjust his motion. And then the third friend, why he's showing an integral behavior. So the third friend looks it. He doesn't give you instructions based on your current position. He gives you instructions observing you for some time, not immediately. So he's telling that you have been walking 10 minutes in this much of an error, just some distance, so that you're in the middle. So it's just like an integral behavior. Uh, and it takes up it makes a PID controller, P proportional, I integral, D derivative. So you can express the same behavior of those friends in a equation of this form. So the error term, the integral of the error term, and the derivative of the error term. And these are like the this sum is a weighted sum of the error terms, the derivatives and integrals of the error terms, and the gains of those, like we can assume, we can define a gain for those terms, and they are represented as kp, ki, and kd. So kp is how much you trust your p, how much you trust your first friend. Ki is how much you trust your third friend. Kd is how much you trust your second friend. So based on how much you trust those friends, your behavior, your system's behavior changes. So what you have heard as PID tuning is you learning how much you're going to trust these individuals. So it's just a idea from the example. It's not too mathematical, but you can see that like that. And the output of this sum is a control signal. Output of this sum is a control signal that you use to control your system. Yeah, that's it. So this PID control system comes in this position, and the outputs, the control signals are directly fed to your plant. This is the like you can imagine this as the system which is open loop. you're you're uh, you're making your closed loop system on an open loop system. It is this plant, and the plant reacts to your input signal to the plant and gives an output. The sensors read that, uh, calculates the error. So the error is set point minus the observed output. The difference is the error. So the error is fed to the controller, and again feeds the uh, open loop system. And this whole thing makes the loop a closed loop one. Right. Going to the mathematical side. So the p term, it's a linear behavior. The p term shows a linear, directly proportional relationship to the uh, p like the a linear relationship to the error. So it's the p term. By the p term, I am telling about this whole term. So this is the I term. This is the d term. So the p term is directly proportional to the error. And yeah, you have we have another example for the p term. It's like a spring. So if you pull the string to a greater length, the force the string applies is greater. If you compress the spring to a greater length, the compression force is greater. If you stretch little, the uh, the force it generates is little. It's like that. And for the t term looks at the error, but not just the error. It looks at the rate of change of the error. So it's a tangent. You can use the uh, differentials, not differentiation, differentials to get this the differential signal for the d term, and it's multiplied with kd, how much you trust the differential, and spits out the d term. So here we have start braking, don't overshoot. Start braking, don't overshoot. And one thing for you to think, what will be the sign of the d term? What will be the sign of this d term? What will be the sign of the d term? If you start at the left of the road and you need to get to the right, and the error to your left side is positive, you are starting in the left, you are going to end up in the middle. uh, we can't directly tell the sign of this d term, because the rate of change of the error can be affected by various factors. It's not just the error, it's the rate of change of the error. So there can be various other reasons that contributes to this. So if you at the start your error term is very high, your p term is very high, but since you don't show a movement towards the center, your d term can be 0, and then your d term can increase. Your d term can increase because you're speeding towards the center, and when you are reaching the center, maybe your reaching speed is decreasing. Your reaching speed is somewhat related to the rate of change of the error, and the rate of change of error can be minus as well. You're still reaching the center point, but your rate at reaching the center point can be negative. So this D term can have weird behaviors. Just I'm telling this just you so that you can think about that leisure. And for micro kind of algorithms, mostly we are going to use the P terms, the P controllers, and the D controllers. We are not going to use I controllers because the maze is a dynamic environment. We are not required to get the exact precision location at the center of the cells because we are just passing cells and we are making turns, and with turns the errors are introduced, but still we are not interested in getting the robot in the middle, but navigating the maze. But because of reasons like that, we are just interested in the P term and the D term for Micromouse kind of applications. There are other types of controllers as well. So PID is a broader set of broader class for the PID controllers. Then we can have subclasses as PD controllers that we are it's the class that we are using for Micromouses mostly. And then we have PI controllers. Not I have not heard of ID controllers, but there can be such things. And yeah, PI controllers, PD controllers, PID controllers. There are various things like that, and it's not the only control. I mean, it's not the only closed loop control system as well. There can be other things, but because of the simplicity and all those things, the Micromouse competitions are going to use PID as a basic control algorithm. Okay, and we have come to the implementation, the code implementation of the control algorithm. So we enter the loop from here. This diagram is a bit incomplete. So the system starts here. The system starts here. It gets an input. It gets an input. The input should be here. It gets an input. The input describes what the user expects the system to behave like. Say the system expect this is a motor control algorithm, and the user expect the motor to spin at 1000 rpm. The loop starts here, and it gets a sensor reading. So it gets a sensor reading immediately. The motor is at 0 rpm. It looks at the user input and calculates the error. With that, it calculates the PID terms, sum that up, and by some sort of another function, it maps this output to the PWM signals that are used to control the motor, and then wait some time for the system to settle and get the speed readings from the motor, and then feeds back to the controller. So this is the control loop for a motor, and the same theory applies for like this is a controller algorithm for the speed of the motor. So there are three things that we can control of a motor: the position, the speed, the torque. Those things can be separate control loops can be run for the motor. So in this case, I use just the speed. Yeah. And you can map this out for your wall following, for your straight line traveling logics, for your motor controlling, for your other robotics projects like robot arm manipulations, servo motor. Like your servo motor is indeed a closed loop system, and uh, I'm pretty much sure it uses a PID kind of thing for the position adjustment. So it's a position adjusting motor, like that. And going back to the math terms, the D term can be calculated as the difference between two error terms. So this is not a differentiation. This is a difference. This is a difference, but it acts as a differential as well. But we can use this for the simplicity. And then for the item, we can just sum up the error terms from the beginning or from a reset. So even though we have sigma e, we can just simplify this to two terms: the new error plus the accumulated error. So you will just need two variables to calculate this item. Yeah, that's it. And this control loop will be running at as Rajinthan mentioned, at maximum at a maximum period of 2 milliseconds, so that you can have a 500 hertz refresh rate. uh, yes. uh, and for the algorithms controlling the motor, for the algorithms converting this term, the ut term, this ut term, and mapping that out to control the motors will be done by Rajinthan again. So over to you, Rajinthan.
Okay, thank you guys there. That was a clear explanation of PID. Before going to the algorithm, I'll just briefly explain what we have learned till now. Uh, so continuously, I'll be explaining how we can control the motors to uh, achieve the desired performance that just following the wall in the center line. Uh, so if you have any doubts or if you need any clarification on the topic that we have discussed till now, just let us know in the chat. Otherwise, so this is our uh, center line. So our mouse should follow the walls by going through the center line. So that's our target. So what we have discussed till now is we can get the readings, the left and right sensor readings, and get the accurate error. So this is the error that we are getting from the both sensor readings that I explained earlier. And what Kavishka explained is the PID controller. So we have the PID controller, but we are neglecting the I term here. So basically we have a PD controller. So this is what we have now. So now what we are going to do is we are going to give this error term to this PD controller. So we are giving this error term to our PD controller. So I'll explain why we are neglecting that I controller in detail on the later part. Now just focus. We are giving our distance error. So if you are on the center, this error will be 0. If you are on the right sides, the error will be a positive value. If you are on the left sides, the error value will be a negative, right? So since we are giving a positive value to this error term, our PD controller will also give us a positive output. So let's take that as a UT. So this will be also a positive value since we are on the right side of the center line. Now we have to correct this error. We have to make this error to 0. So how we can do that? So we have to use this uh, output duty. So we assume that duty as the output from our PD controller and feed this to our micromouse. So here's our micromouse, and we have motors on the right side and the left side. So we are just going to feed this to our plant. So our micromouse is the plant, and what we are getting back, then again we'll get the sensor reading. So that's our feedback. So and then we are subtracting that or doing some math here to take the error value back, right? Our intended target is 0. So we have to make this error to 0. So this is what Kavishka explained. So we have his PID controller, and this is the error term that uh, I explained earlier. Now, what we are going to do, we have to give our output to our micromouse. So in on micromouse, we have to control only two things: the right motor speed and the left motor speed. Okay. So take this example case. So here we have a micromouse on the right side. So to correct this error, we have to move our micromouse towards left side. For that, we only have control to our two side of wheel speeds. So now what we have to do? We have to move towards left. So we have to increase our right wheel speed and decrease our left wheel speed. Then our mouse will automatically move towards left. So what we have to do? We have to give this duty plus u of t to our right wheel speed and negative u of t to our left wheel speed. So we are increasing our right wheel speed and decreasing our left wheel speed. So this is how we align our mouse to towards the center line. So if our error term is negative, in this case, our error term will be negative. So our duty will be also negative, and if duty is negative, our right wheel speed will decrease and left wheel speed will increase. Why? Because we are subtracting our negative value. That means adding a positive value. Okay, so that will leads in the mouse to uh, move the mouse to the center. Okay, so that's our desired output from our PD controller. Actually, we are neglecting the I, so that this is the actual output if we are using our PID controller. But here, what's the problem? We don't know what are the coefficients for P and D terms. Okay, uh, I'll continue from the algorithm. Okay, so here you can see, just ignore this first line. Focus on the second and third line. So here you can see that we are having our base speed. In example, we can have a 30% of our maximum speed, and we are subtracting our output value from our PID. So this correction value is the output value from our PID controller. So we are subtracting that from our base speed and giving that value to our left motor. So the similarly we are adding our PID controller's output value with the base speed and giving that value to our right motor speed. So by doing this, we can make sure the mouse always move towards the center line. But here we have to, the problem is we have to figure out the KP and the KD parameter values. So this is where most people fail and blindly tuning these parameters to render numbers and uh, just getting bored and giving hope on the Micromouse. So that's why I'm going to explain how to do this in a proper manner. So first, we always start with the KP value. I already explained that we are going to neglect the item. We are going to just uh, we are only focusing on the KP and the KD value. So first we start with KP and KD as 0. Then we start raising the KP value until we get a allowable oscillation, right? So if we have our KP too low, imagine you have just place your mouse on a very uh, straight path with two walls are there on both sides. So you at least have a 5 to 7 cells with both walls. So you start your mouse here and make it to run this way. Mm, so you place your mouse here and make it to run this way. So what will happen because of the friction mismatches or motor torque mismatches? Your mouse naturally move towards to one of the sides. So if your mouse always move towards one of the sides, that means the KP is too low. Even if you have a perfectly matched motor and friction and everything, you can just place your mouse with an angle error, not not parallel to any of the walls. So your mouse naturally go towards a side. So what should it do? Actually, if you have a correct KP, it should correct the error. So if your mouse move towards this way, your mouse should correct the current positive error and move towards the center. So that's where you validate whether you have the correct KP value. So if you slowly increase the KP value to some extent, you might find that it always overshoots. Like that, if the mouse is in this side and measures the error and turns violently towards this side and go passing this center line and overshoots. This means you are having hit too much of KPI. Then you have to balance the value by trial and error. So this is the fastest way other than using MATLAB or other tools to find the perfect value. This should be the fastest way. Actually, I use this way to tune my mouse. So in this way, you can tune it within minutes. Actually, it won't take much time. So if you only two cases. If you observe this behavior, you have to increase the KP. If you observe this behavior, overshooting behavior, you have to decrease the KP. Then get to an extent like this. Okay. So now you're not worrying about KD at all. You're only focusing on KP. The other values are 0. Now, after getting a smaller oscillation from your micromouse, then you can move towards the KD. So now you are having a stable oscillation after getting a correct KP value. Now you can move to KD. What happens if you have too low KP value? Your micromouse will just follow the KP and have a smaller stable oscillation. What happens if you increase the KD too much? K, the KD, um, okay, the KD value is calculated by the differentiation. Okay, so if you increase the KD too much, in in ideal case, you will get the exact distance offset from your center line. But in the practical cases, you will have sensor noises, reading noises, sampling noises. There will be so much noises added to your sensor. So if you take the derivative, that noises will lead to too much value from the derivative value. So if you multiply that with a constant with a large amount, like the KD is too much, then that number itself only increase to a very large amount. that will overcome the other parameter like KP or KA and have the effect that directly proportional to that noise factor. So you will have the high frequency jitter. So if you increase the carry too much, you will notice your mouse is vibrating like this and might overshoot and just hit the wall sometimes. So that's where you can identify your KD is too much. So if you have a right amount of KD, you might find that it will start with this small oscillation, and the oscillation will decay over the next few cycles. If you have the perfect KP, then it will damp in the very next cycle, so you will have a perfect response. But you don't have to focus on perfecting things. Just you can uh, stop at this point. So you can focus on other things and you can spend time on other things. So you don't have to perfectly damn this thing. Okay. So this is how you tune that. So only by doing this, you will have the perfect performance, the better performance on your Micromouse. So you can take a screenshot on this. So you can use this. So this is just the same thing I explained in the previous two slides. So you have too low KP or too high KP. What should you do? Okay, and also then after tuning your KP and carry for a certain speed, just test it on the 60% base speed. So if you tune that on 30% base speed, you can try increasing the base speed to 50%. Then try tuning the KP and carry once. Then you can verify your mouse and your everything, your KP carry release now okay with you. Because if you change your base speed or your battery voltage changes, the tuning parameters might have some effect on the performance. Okay, so just verify that also. And I have to give you some tips while doing this. So I also faced these issues and found those by doing some research on that. And it took me sometimes it took some days. So it would be very helpful if you have these in mind and doing the uh, development. It should save you a lot of time. So first thing, the battery drop. So always you can't assume you have this stable power supply with a constant voltage. In example, if you start with a 2 cell battery, the initial voltage will be 8.4 volt at a fully charged battery. But if it's dropped, it can be dropped to even 7 voltage. So 8.4 to 7 voltage. There's a 1.4 volt drop. So even if you provide the same amount of PWM pulse width, you will have different speeds on the motor. So you have to be careful on that. Uh, there are some other techniques like feed forward techniques for driving the motor at same speed, even the voltage drops, but it might be too much for starting. But make sure to have a freshly charged battery all the time, or you can swap the batteries on each run, so you can make sure the battery stays around 8.2 to 8.4 volt all the time. So that might be very easy. And even the surface can determine your performance. In a four-wheel mouse case, the friction can affect, but that's not a uh, very important thing to consider. And the very important thing is the loop rate matters. So if you have the PID, so in example, you are calculating your sensor, like you are taking your IR readings and calculating the distance and giving it to your algorithm, PD algorithm, and calculating the output value and updating your uh, PWM for the motors. So this is the whole cycle, and you have to do it this several times. So this after updating your motor, your sensor readings will change, and you take the sensor readings again and calculate a PD output and update your motors again. So this will happen. And while you doing this, you have to do this very fast, and you have to make sure you know how many times per seconds this is happening. Usually, people make this more than 200 hertz. So in my case, I did this at 1000 hertz. That means every millisecond there will be an interrupt triggering the sensor reading. So every millisecond, the sensor reading will be taken, the PD value will be calculated, the motors will be updated, and then it goes into a sleep mode or doing something else like calculating the uh, path for the maze center finding or anything. And then after the very second, after the second millisecond, it again fires up. So the sensor reading is taken, and all the other rest of the things will be done. So you have to make sure you have a very stable loop loop frequency. If you just blindly do put everything on a while one loop and get the sensor reading, uh, calculate the PD, and update the motors. If you do like this, you don't know at what speed this loop is running. This can vary according to the other processing load. Like you can, there might be some other interrupts running in the background, so this that can affect this loop. So it can vary from 200 hertz to maybe 2000 hertz. So it can vary. If that varies frequently, then you don't get a proper PID proper smoother performance from your Micromouse, because the PID controller can't handle these much of nonlinear effects. Okay, so that's why it's really, even if you run your PID loop at 100 hertz, that's fine if you have a stable 100 hertz PID control algorithm, right? Always make sure to have a constant update frequency on your PID algorithm controller. So that's really two matters. This is very important. Okay. Then the sensor noise blows of KD. As I said earlier, the sensor noise, the KD for the D parameter, we are calculating the derivative term. That means if we have a sensor reading like this, if it increasing and have the noise performance, we are calculating the D term by subtracting one value from the current value, the previous value from the current value. So we might end up with only calculating this noise, the steeper noise part. So that might end up in a very large detail. So to avoid that, it's recommended to have a moving average filter. So you can have a digital filter by in the algorithm, just a simple moving average filter. You can search for moving average filter, and you'll find a simple equation for that. That will result in you in a very smooth sensor readings after the filter. So by adding that, you will get a very smooth sensor readings, and you can feed that into KD, and you can have much smoother performance by increasing the KD value. Otherwise, you will have very high frequency oscillations like jitters on your mouse performance. So this is also pretty important, but sometimes it might be very too much for the first time Micromouse builders. So you can use only the P term for uh, wall corrections. And if you want to increase the D term too much, you have to implement the digital filter, moving average filter for your sensors. Okay. Then the wall loss, as I mentioned earlier, you might have two walls or only one side wall or no walls at the time. So you have to find whether there's a wall or not, and make click the sensor reading where there's no walls on the side. Otherwise, you will have very bad performance on this. In this case, if your mouse is moving from one side wall case to two side wall, you should not have different error scenarios, since it's always on the if it's having a 10 millimeter offset error, it should give the same error value for both cases. That's why we are multiplying the error by 2 on the one side only wall case. Okay, so these are the main practical problems you might face while building your micromouse. So just just make sure to pay close attention to these issues. Okay, then so if you are done with the sensor readings and if you understand the PID algorithm, actually it's PD algorithm, you can start implementing the C code. So here you can see the C code for the PID. So here you are only having 4 lines of code, so that's actually enough. First line you are getting the error. So this is the compute error function that I discussed earlier. I think I can show you once again. So this is the compute error function that I discussed earlier. So here you are handling all the 6 cases by categorizing them with the right wall presence and left wall presence and returning only the error term, the indent, the error term calculated from the mismatch from the center line. So that's what this compute error function will return. So this will only return the error term, how much you are deviated from your walls. So if you are on the right side of the center, you will get a positive error term. Even if you have both walls on the side or a single wall on the side, you will get a positive error. But here you will multiply this by 2, so you will get a same error value for both cases, even if you have even if you have side wall or two side walls, you will get the same value and positive error for right side error. So after calculating that error, you are having this single variable error. Now, what you have to do, you have to find the derivative also. So, how do you calculate the derivative? Mm, if your error is moving like this, you store the previous error on the previous iteration. Now you have this error. This is the error now you have. Now you are calculating the derivative by finding the difference and dividing it by the time. So for that time, you always know that you are updating your loop at a which frequency. In my case, I am updating it at 1000 Hz. So I know that the DT is 1 milliseconds. So that means 1 into 10 to the power minus 3. So I have a constant DT. So I can have this as a constant 1 millisecond. So now I know the derivative term. So on by only using this error term and derivative error, I can calculate the whole PD value. So here I'm multiplying the error with the KP and the derivation of error with the KD. Now we only have to tune these two values. That's it. So that's what I explained in these two slides. So here you can tune the KP to get the mouse performance like this and KD to get the performance like this. So you only have to focus on those two parameters. That's it. You don't have to worry about anything here. Okay. Then after getting the duty, so this is the PID wall flow function. So here you are giving the distance values as input, and that is used by this function to get the error, and you are only getting the correction. So at the end, you are getting the correction. That's what uh, Kavishka told us UT. So UT is your correction. Now what do you have to do? You have to subtract that UT from the base speed and give it to the left motor, and add that UT to your base speed and give it to the right motor speed. So if you feed the motor's PWM with these two values, your micromouse should always follow the walls by going into the center. Even if you have both walls on the side or only have one wall, or you might miss both walls on the both sides. So if you place your mouse like this and let it to run, it will always automatically goes to the center and follow the walls automatically. So this should be your final behavior. So this is very much important for the micromouse to uh, go forward with the path pathfinding or any other algorithm. So at the first step, you have to achieve this performance before moving forward. So even if you have two walls or one wall, the micromouse should always follow the center line without much jitter. Then you're good to go with the further high level algorithm implementation. Okay, then I can show you the same mouse performance that I built with all these PIDs tuned. And on top of that, I have a flow fill algorithm to find the path and then it will do a fast one. So this is the performance of the fast one. So here you can see, even if that has both walls on the side or only the one wall, it is following the walls by being in the center. So in these cases, it only have one wall on the side, but it's following without any issues. So even if it goes off from the center, it automatically adjusts on the very next cell. So it only uses one cell to adjust to the center. So it can adjust the errors even if goes beyond the center, and it can be adjusted by only going through one cell. So this avoids collisions on the next cell. So this wall following algorithm should be very perfect for the overall mouse performance. And here I have used the uh, gyros for some alignments, but I haven't discussed about that in the PID explanation because that might be too much. But the idea is the same. For the PID controller, you can use any sensor readings to align to the wall or align to the line. The idea is the same. If you know how to tune the P and V, then you can do it. You can tune any mouse, any micro mouse or any line follower without any issues. And also, if you want to have a look on how this micro mouse is made and what are the components, how the circuit works here, and what are the 3D parts here used, how the development worked, and what are the components that have been used in this micro mouse, and also the algorithm uh, that runs on this micromouse brain can be also found in this repo. So if you want to explore more about this micromouse, you can just take a screenshot of this QR code and let us scan to find the open source repository. Actually, we have open source this micromouse, so anyone from Sri Lanka can build it on top of this and compete in competitions. So have a look on this repository for details.
I think this workshop might have cleared your questions about PID and sensors, how the PID should be implemented, what are the inputs that you have to feed into, and how we should handle the output, and how
How
we
you
should.
should feed that back into the micromouse. I think it's clear about that. Mm, all the best for your competitions. Thank you.
You can ask your questions by simply scanning the QR code that is displayed on your screen. So this will take you directly to a slider where you can submit your questions in real time.
Also, can you put the slide or link in the chat? Okay. Someone asked about the moving average filter. So it's not a complex topic. It's even simpler than PID or getting any sensor readings. So what the moving average filter is? Uh, so if you're having a sensor reading like this, uh, so usually your ideal sensor reading should follow like this, a smooth curve. Okay, but because of the additional environmental noise and your ADC noises, you might get readings like this. So it always follow the ideal sensor reading, but they add some noise on top of it. So that's why you have to implement the moving average filters. In simple explanation, you can assume that you are adding a certain period of readings and getting the average. So as you can see, the reading is above, like it has positive error and negative error. If you add everything together and take the average, you will get the error cancelled out. This negative error and the positive error is cancelled out. So you will get the same exact reading that follows your actual sensor reading. So this is how the moving average filter works. Why we are calling this moving average? Because this window is moving. This window is always moving through the time while we are getting reading. So we get the average on this window and take the sample and take the reading. Then we move the window on the next sample and get the average and take the reading. So that's how it works. That's why we call it moving average float. So it's very simple. If you're having your sensor reading as, if you take the sensor reading as XT, you just multiply with it a constant alpha and add it with the 1 minus alpha into your previous reading y of t, and this is your, so this is very computational uh, efficient. So you're only having two multiplication and one addition. So this won't take any extra extra or any much of computational power. So you can run it in thousands of hertz. for any all sensors. So this is how you implement the moving average filter. So for this case, you have to only fix the alpha. So this is depends on your sensor noise and your response time, everything. Usually, point 6 to point 9 is point maybe okay no, sorry point 8 to point 95 or point 99 should be fine because you are getting samples in thousands of words. So you can run it at, you can keep it as high, very near to one. So you can get a fast response while having less noise. So this is kind of a trade-off. If you increase this, you'll get fast response, but uh, some extra noise. If you decrease this too low, then you will get a slower response, but better noise performance. I hope that explains your question. Okay, the question is, can you explain the process of calibrating IR sensor? Sure. So that's what I explained earlier. So you basic usually you play so different. There are not only a single method to calibrate it. There might be different methods. So in my case, I just used a simple method. Uh, I placed my micromouse in a three-side covered cell and I measured the forward distance with a ruler. So I placed the micromouse 5 centimeter, that means 50 millimeter apart from the front wall, and placed the micromouse exactly in the center. So I know all the distance from the micromouse sensors to the wall. Now I'll use take the readings, like 1,000 readings, and take the average. So now I have the average ADC value. Now, as I mentioned earlier, this is nearly equal to k over d square. So I have the average ADC reading. I know the distance because I placed the mouse to a known distance. Now I can find the k for all four sensors. So I should have four k values. Okay, so I found the constant stored in the permanent flash storage. So I can use this for all the other runs. That's how I calculated sensor. So using this K constant, I can calculate the exact distance on the all the runs. So for different sensors, this calibration technique can differ, and also even for the same sensor, some people run their micromouse uh, in position and make the micromouse to rotate, so they can get different set of readings on different cases, and they will use that to calibrate the sensors. So it can be can differ to people to people. I think getting rid of the ambient light I've already explained in the previous slide. So you can get the readings for turning on the IR LEDs and get one reading after turning on the IR LEDs. Just subtract one from the another. You you will get rid of the ambient light. And the motors and other component details are in the repo. You can just follow the QR code to get the details about the components that I have used in the Micromouse. Okay, we choose to use TOF sensor instead sharp IR sensor. We don't need to calibrate again and again then, isn't it? Because of we measuring actual distance. Okay. Actually, the top sensors are good for measuring distances. So in I think you assume that I'm using sharp IR sensor. I'm not using sharp IR sensor. It's just the IR LED and the photodiode. So this is faster than sharp IR. Uh, but does not give you an exact distance reading. But if you use stop, yeah, as you said, you will get the exact distance reading, so you don't have to calibrate against the wall. But the main problem is you will take 20 milliseconds to take one reading. So maximum uh, PID loop you can run is only around 50 hertz. So that's the main problem. In my case, I'm only using an IR LED and a photodiode. So this is very much fast. It only takes 800 microseconds. That is less than 1 millisecond. So it's 20 times faster than top. So I was able to run the PID control loop at 1000 hertz. So that's the main advantage of using the IR LED and the photodiode pair. I hope it explains your question. Okay, that's it. There's one more question. Can we get the today's slides, please? Uh, I think I can share the slides. Uh, I think I can share the slides with Lakmina so he can share with you guys. Is that possible? One more question. Um, can we determine what cell we are in? Measuring the distance traveled may not be accurate because of some oscillation is in the trial. Yeah, you're correct. This is actually a good question. So sometimes you might face uh, cells in a row, like 10, 12 cells in a row. So there might be 12 or 10 cells in a row. In that case, uh, there's an issue called if you are missing some 2, 3 millimeters per cell, then you'll end up in having a 30 millimeter error in 10 cells, right? I think that's the question. So in that case, you might uh, get into the next cell with a very large offset. So maybe if your error is more than 5, 10 millimeters, then you might miss a cell. You might count that as uh, an extra cell, or you might miss a cell. So that will result in position estimation mismatch. So there are different techniques to accommodate that. So usually in each cell you will have a pole, right? So if you are using the IR sensor, actually you can differentiate the reading while passing this pole. So, but this is uh, too much for a beginner. Actually, you can use that to estimate whether you are passing different cells or not. But this is actually too much. The other easy way is you can have a uh, calibration technique uh, by using the motor encoders and spinning the two at some extra offset for each volt. So you can basically, if you run in a straight line, you will pass 100 millimeters. If you have some oscillations, you might go 102 millimeters. So you can add that extra 2 millimeter in a variable by having a settings menu in your Micromouse and use that to uh, recalibrate your cell counting mechanism. So that is the easiest way. But if you go for the sensor based detection technique, that will be too much. So I recommend recalibrating with the variable should be fine. So you can add extra 2 millimeters for each cells while running. So you can make sure not to miss any cell or extra counting the cells. I hope that is clear. Okay, I think the questions are all the questions are have been answered.
Thank you for that insightful session, Mr. Kavishka and Mr. Rajinthan. We would like to present this token of appreciation to Mr. Kavishka Jayakody in recognition of his valuable contribution today as a guest speaker at MazeX 1.0 Workshop 3. Your insights, knowledge, and time have truly inspired and guided all of us here today. And also, we would like to present this token of appreciation to Mr. Rajinthan Rameshkumar in recognition of his valuable contribution today as a guest speaker at MazeX 1.0 Workshop 3. Your insights, knowledge, and time have truly inspired and guided all of us here today. On behalf of everyone here, we would truly like to appreciate your time, effort, and valuable knowledge shared with us today. So, before we wrap up, we'd love to capture this moment with all of you. Could everyone please turn on your cameras and switch on your virtual backgrounds for the group photo? We'll give you a few seconds to get ready. So we'll take a snapshot on the count of 3. 1, 2, and 3. Thank you. So, as we come to the end of today's workshop, we encourage all of you to stay connected and continue this journey with us. There's so much more coming your way in the upcoming sessions, and each one will build on what you have learned today. Whether you're here to compete or to learn, your consistency will make all the difference. Stay motivated, keep exploring, and we look forward to seeing you in the next session of MazeX 1.0. Thank you.